So in this third part of our session today, I would like to talk about the problem of approximating a function, an operator, so a matrix by a Gabor multiplier. And as you see from the help file, the input is the operator or the matrix, and the natural argument would be, well, please do an approximation with a Gabor multiplier using the ingredients G and A and B. So we could say, well, use the tight atom because that will have good chances to do approximation. But with such a routine, you can compare, well, if you change the window, do you have a better approximation or so? Now, if somebody is asking you, can you do an approximation Gabor multiplier? Then of course the output should have two informations. I mean, the first one is, what is the Gabor multiplier itself? So then we can look at the difference of the two operators and so on. And secondly, how do you compute the Gabor multiplier? And there are other informations about Gabor multipliers. And for this, you need coefficients. So Gabor multiplier is actually a linear combination of the projection operators on the atoms. And that's why we should check also on this. So I was just quickly checking this routine. If I take our Gabor multiplier, which was created from the tight atom with lattice AB, then of course the best approximation, which was the GMA, should be the operator itself. And in this example, at least, this routine works well. Now, again, if you're taking the Gabor multipliers, we have seen that for decent lattices and by using the tight Gabor atom, you have already very good approximation. But now the question is, well, if I approximate different operators, do I get similar operators, sorry, A and A1 and A2, do I get similar Gabor multipliers? Or is this approximation quite unstable or so? And to summarize the fact, of course, I'm saying, well, what we have to look for is the collection of all the projection operators, which are on these 720, in our case, 720 Gabor elements. So for each of these elements, we have this, and they turn out to be a linear independent set, actually a re-spaces for the linear span, in the space of matrices. So in the continuous case, you would say, oh, they're rank 1 operators, your projection operators you project onto the atom number 27 or so. Now these Gabor elements have some separation, and also they are linear dependent, and it's quite surprising at the first sight. You have 720 elements which are clearly linear dependent in the n-dimensional space with n equals 480. Their projection operators are still quite nicely and linear independent. So the condition number of these things, and I don't discuss for quicker discussion the condition of how it is computed, but let me just say, can compute it. In this case, the condition number is less than 6 in our case, which is quite nice because it means that's quite stable. That means if you're getting two operators which are not too far away by epsilon, then their corresponding best approximation by Gabor multipliers will be also very close to each other. Now, the same routine, this conditional number of the projection operators, can be used for general lattices. So either my input is AB, then the lattice will be our standard lattice, or you take some other lattices, and I was choosing 3 alternative ways to create slanted or side lattices. So side digmat, side to mat is the inverse, and imp to in is another inverse. So in this way, if you want to see these lattices, let me just see. So we can do all these things, of course, for oblique lattices, but let's do this side digmat of lambda and imp to in lambda. So imp to n is a command used by Werner Kotzek to create, to compute the Korn-Nirenberg symbol or the spreading function, I don't know. But it just says, well, if you have a matrix which is constant along the columns, so you have 1, 1, 1 in the first row and 2, 2, 2 in the second column, then you put the 1 into the main diagonal. So it makes a shear operation. And if I look at this now, the result will be some lattices. Hopefully, and you see they are a little bit sheared in one or the other direction or so. And you see that the condition number on the family of projection operators of these is a little bit better, and I'm quite sure that probably the two lattices that I get with cyclic mat and imp to in are the same, because these numbers look suspiciously similar. So why is this relevant, or how can I understand this phenomenon? And the question is, yeah, maybe we look at the projection operators, and we look at so I'm showing you what is the relevant fact in the background. We look at the Korn-Nirenberg symbol matrix to Korn-Nirenberg symbol of the projection operator, and we know that projection operator means first you take the projection here, so you can call it PGG. The projection operator is just this scalar product, because I'm taking first the scalar product with this yeah, and we are not very surprised that this actually is a Gaussian. Maybe we do a strong zoom. So the Korn-Nirenberg symbol is a Gauss function. And so what we're actually doing is the following. The routine is based on the following observation. Assume you have any operator, and you would like to approximate it by, yeah, maybe we do even something more. We do this Gabor multiplier stuff, and I show you how the different representation of a Gabor multiplier look like, and we have this GMW. Hopefully this works. No, sorry, that was the wrong. So recall, it was not necessary. We should look at the plot, yeah. It's very faint, and I should do subplot 2 to 1 and do zoom here and subplot 3 zoom chart as well. Then we will see that first of all, this Korn-Nirenberg symbol looks interesting. It looks a little bit like a smeared version of our weight. So that was the weight here with a peak in the center in my example here, and this is somewhere here. So everything is smeared. It's more blocked. The matrix itself is very much concentrated here, and it turns out to be a multi-diagonal case. And also in the Fourier version, it looks a little bit more thick, but that's fine. And the spreading function is so small that you cannot even see it here. But okay, there was a typo, subplot. That's why it didn't work. Yeah, maybe I should also do subplot 2 to 4. Yeah, that was of course wrong. It should be 2 to 2. And this should be 4. I do even stronger zoom here. So maybe now hopefully we can see more. So a Gabor multiplier is not a diagonal matrix, but very close to a diagonal. In the Fourier version, you see it's a little bit broader. And of course, it's no problem to say that even tridiagonal matrices have about, roughly speaking, 3n entries, and why shouldn't 2n or 3, I mean, in our case, 720 tridiagonal matrices being linear independent. So that's quite possible. And so that's why the condition number is okay. And here it's too faint. Yeah, I think we should look at the spreading function even closer, but I will do it separately. So the point is, yeah, maybe we do this spreading function of Gabor multiplier with weight. So a new figure to show how concentrated it is. Maybe a little more. And what was the G? Not C, but G. Gabor multiplier with weight W. And then you will see it's very concentrated. Oh, I'm too sloppy now. It's very concentrated near the origin. So in the spreading domain, it's just constituted, yeah. It's constant, it's near 0, but it's also, no, it's just, yeah, that's not the spreading function, it's the operator. So you see the tridiagonal structure, so to say, but I wanted to show you the spreading representation, because that's why these Gabor multipliers were started from the beginning. If you have an operator where the spreading function that was too much is very concentrated, then there are good chances that you can represent it as a Gabor multiplier. Yeah, no, I think it's fine. But on the other hand, what you also see that the Gabor multiplier has a periodic repetition of the spreading function. So essentially, if your operator has a spreading function which looks like this, then you have good chances to represent it as a Gabor multiplier. Now I should go back and just tell you what the intuition is. We want to approximate an operator where you have a smooth Korn-Nirenberg symbol by shifted versions of this two-dimensional Gauss function. So you can imagine that with such bump functions, you can create a good approximation at the rough scale, but not at the fine scale. Now I do the same thing in 1D. So let's talk about an approximation by a system of translates. So you could do the same story with B-splines, then the Gauss function would be replaced by a cubic spline, let's say, a function which has compact support and which is glued together from pieces of cubic polynomials in such a way that you get a C2 function, or I take my discrete Gauss function. Now, if I take the translates along the lattice A, which is 20, I get this family. Remember, you like to use families which are families of row vectors. So 24 vectors are here as row vectors, but plotting requires to take the prime, turn them into column vectors. I could also take the same family, but with a much smaller lattice constants 8. And later on, I will take some more. And then I'm asking, what is the condition number? And the condition number of the displayed family here is, maybe I'm doing also one decoration. I make a grid and make axis tight. Hopefully it works. Yeah, see, it's a bit more beautiful. The condition number here is less than 2, which is perfect. Very nice. But if you take the lattice constant smaller, then you will say, yes, of course I have more elements, but the condition number is suddenly 255. I could take an even larger lattice constant, like 30, then you would say, okay, it's getting closer to 1, which means such a family would be almost orthogonal. So clearly, if you would have B-splines where the support size is not too big and you make big lattice constants, the shifted B-splines would be disjointly supported. Therefore, that would be a perfect orthogonal system for the linear span. But of course, now you have the problem that if you take too many positions, then the correlation is increasing more and more. They're getting almost linear dependent. You can replace one of the very narrowly spaced Gaussians by a linear combination of its neighbors. But on the other hand, you think that you have more spaces, and they are the nominal way. If you give me any finite collection of Gauss functions, they are linear independent in the sense of linear algebra, but of course not in the numerical sense. So to give you an idea, it was just to compare two eigenvalues or singular values of such families. In the first case, I take the fine family, which is lattice constant 8. So you see it starts nicely, but then it goes down, and which means if I want to represent, let's say, 40 dimensions, I will find some vectors which can be represented, but where the cost of representation is quite high. So one could look up these things and you would see that would be a function which is maybe something a little bit more narrow than a Gauss function. And then you need alternating signs and badly conditioned approximations. Now, if you take the small family, which was original, this plate family, the situation is much better. So the condition number is getting worse, not because the upper condition number is exploding, but because the eigenvalue, the last singular values are getting so small that the quotient is getting big. Now, I wanted to show you this. So this is still just a one-dimensional analog of the situation that we have in yeah, that was not good. Start a new figure. So I'm saying, well, if I want to approximate a function, then it has to be, of course, smooth. So somehow looking at these building blocks and the fact that here, what maybe in space dimension, these are, even in the linear algebra sense, 24 linear independent elements. And now I'm taking low pass signals which look like this, and the maximal frequency is 12. Yeah, actually it could be a nice object to say, well, yeah, maybe let's play around here. What is the dimension of the space of such low-pass signals? So this concrete example will have a reasonable good approximation, but the projection on this family, so TRLGA is the family. Where is my command? Yeah, the projection on GA is first I have to take the pseudo inverse of TRLGA, and then I have to take the synthesis operator, which means linear combination of the GA. I want to convince you that the PGA is really a projection operator. Yeah, and then I want to convince you that if I apply this to the family, so to each of the elements of the family, of the original family, so that's multiplied from the right, that each of those vectors, therefore the linear span is preserved. And there was a typo apparently. And you see that this is really the projection operator on the linear span. And now I'm taking the signal XXPAG is just XX with PAG, and the difference is XX minus XXPAG. Now let me look at the differences here. So I'm doing F to spec of XX P, and maybe the original versus the projected one, and afterwards figure Also here, figure. Afterwards, I'm looking at the difference. Plot C. What was the name? XX different, I wanted to say. Difference. I have to correct it. So essentially, it's clear that because the space of the low pass signal has dimension 25 and the projection is on the 424 dimensional space, there must be one such signal, a one-dimensional space at least, if not more, which is not at all reconstructed. But there was a typo. So let's just, and also let's check whether the command here is doing my best approximation is really giving the same thing as this projection, which normally you shouldn't do such a build an operator and apply an operator to an individual matrix. You should have a fast code, but let's try to do it here. Okay. Oh yes, so the GA was also here, not here. And key GA, so yeah, that was nonsense anyway. So let's see if there are more typos. Yeah, so you see there is no big difference. Visual inspection tells you it looks very similar. Well, in this area there are some fine tuning. But if you look at the difference or so, it has a small scale, but it seems to be mostly concentrated at a particular frequency. So you could imagine that this is, of course, the maximal frequency, which is badly represented here. Now, to come to an end, let me say that if I do now this routine, and you see what I'm doing with the projection operator is this routine doing. So the best one-dimensional approximation of a one-dimensional signal by the shifted versions of my atom G by the lattice constant A. And I will look at the error. So the error with lattice constant 8 is, is XX8 is the approximation. So let me first look at the approximation of this here. And you see this is the norm, the size of this here is still significant. If I increase the number of Gauss atoms or I decrease the lattice constant 8, the condition number will be worse and the approximation error will be much smaller. But if you increase it further, I didn't put the condition number here, you get an even worse condition number, but the approximation is not significantly better. So what does it tell you? That if you have these Gabor multipliers, the question of approximating a Gabor multiplier in the Frobenius norm sense or as a Hilbert-Schmidt operator is the same as doing sorry, an L2 approximation of the operator by of the Korn-Nirenberg symbol of the operator by the shifted versions of the Korn-Nirenberg symbols of these atoms. And therefore, let me see, this is something I should maybe try to mention here. I'm not sure I prepared it elsewhere. So we should maybe just say, there is a operator called pi tensor pi star. So, well, let me do this. G35 is is just a time frequency shift of my Gauss atom with 3 and 5. And then the projection operator on this is just G35, turn in the column vector, and then with G. No, it's not good to do this because I need conjugation. So now it's not real valued anymore, I have phase factors. So it's G35 with G35. Just to check once more, that this is a projection operator. And I think you will believe me that it's a projection operator onto the element scalar multiples of this here. What I want to show you is this, that we can also use a routine which is called pi star. So in symbols in the article of Werner Kotzek, so in the BibTeX file is the paper with Werner Kotzek from the Brown book. We have another way to compute it, and we will say we take the pi star with parameters 3 and 5 applied to the projection to the Gauss function 3 and 5, and that should be the element on this here. Oh, no, this is not necessary. Here the bracket is too much. Yeah, see, this looks fine, and therefore I want to demonstrate only one little thing, is that if we take now the Kohn-Nirenberg symbol, so the KPGG is the mat to Kohn-Nirenberg of the projection operator, and we've seen this looks like a two-dimensional Gauss function, and we can take the PG. Well, that's right, GG35, which is a mat to Kohn-Nirenberg symbol of the projection operator PG35. And then the claim is that they are just obtained by shifting one by the other. So I'm making a comp norm between this the Kohn-Nirenberg symbol of the projection operator on the element from our Gabor, that could be an element from our Gabor family. So instead of 3 and 5, I could take 2a and 5b or whatever. And now we have to do shift in the time frequency plane, but we are having functions on time frequency plane as matrices. So it should be row and column of this Kohn-Nirenberg symbol of the original one, and now I have to guess. Rotate in rows and columns, and the time shift is 3, which is horizontal. So I guess it will be the second parameter. So let's try to do it in this way. You see, I'm even not remembering the details, but if it's not correct, I would just copy this line and try, first of all, I mean, we could try to do this 5-3, and you see it's in this way, it's working fine. Well, it's really the question, what does it mean rotate rows and column? Are you rotating the rows and change the order of the rows, or are you rotating within each row? And so the rotate, yeah, maybe we try to do this. Or the standard example is the test matrix of size 5. And if you want to rotate rows and columns of this matrix by 1 and 2, we will see what it does. Rotate column rows, I think also exists. And to do this 1, 5. And of course, I should mention that I'm working in the row column mode, being the rows. So I'm in my usual way. Otherwise, the functionality will be different or so. And then you clearly see that this, so maybe this doesn't exist, but this command means rotating 2 is the column index. So a matrix is described by height of, which is count, I mean, element A35 is third row, 5th column. So first comes the row number. So I'm rotating, it's difficult to say. I'm rotating 2 in the second direction, which is the column number, and I'm rotating 1 down. So I'm moving my 1 first down by 1, and then this. So the order of this command is row column, means first how much cyclic shift do I have with the row numbers, and then how much cyclic shift I'm doing this. So cyclic shift of row numbers first and column numbers then. That's how we have to interpret it. And this is actually the trick how you compute a Gabor multiplier, because it would be quite cumbersome to create all these projection operators. I should have written a code or prepared a little code saying, you can take all those 720 elements, you create the projection operators, and then you multiply them with the weights. Maybe I had it in the earlier code. And much better is it to say, no, I have to have these shifted versions of this PGG, of the Korn-Nirenberg symbol. Now I do a linear combination, and this can be done by FFT. And actually also the condition number is using the lattice structure. And it's not important that our lattices are the concrete lattices with A and B, but with other lattices. So just to indicate the idea of the compound condition number, here I got stuck with my quick preparation, is to say, well, what is a good Gabor family? Well, a good Gabor family is a family which allows us to approximate good operators, namely the so-called underspread operators, by a Gabor multiplier. Now, what is a good frame? Well, a frame which has a good condition number, where the dual atom is very well concentrated, or better, where you can find a tight atom very similar in terms of shape to the original one, which allows you to do the approximation. Now, you would also like to have the approximation good, so the idea of the compound condition number, and I still have playing around to find a good solution, is to say we have to balance the condition number of the family of projection operators. So recall in our case, we have a condition number of the Gabor frame matrix with atom G and A, B, and the condition number of the projection operators coming from such a family. These have to be in a good balance, and in our case, yeah, what's wrong here? I don't know what I've done. Oh yeah, I said the matrix, the word matrix is wrong. So if we look at the condition number, they are both, and therefore maybe their product is fine or so. Now, my first proposition was to say maybe we should take the geometric mean as a quality measure. So if you go through the lattices, we should get a perfect balance between the stability of the approximation of the Gabor multipliers and the frames. But if you play around, and we have seen, if you get the tight frame, I mean, let's play around here with the T, and of course, you get perfect reconstruction, and therefore it's yeah, you can do this here. So a tight atom is always better if you take the product or the square root of the product of this, because I have even improved the condition number or so of the projection operator. So, but if you go through this in a different way and you put different weights, it's clear that the second number is only small if the redundancy is not too big, and we're just coming back to this area of interest. So I think I should say, well, we could take those, in our case, 35 lattices, and compute the compound condition number in order to find the ones. And what I found out that the ones that I would use based on my kind of personal experience with all these examples would be, I stay away from the critical one and try to do this. To choose a stable, I stay away from this here because high redundancy means very bad condition number for the projection operators. I stay away from the very eccentric ones because they would have very bad condition number of the Gabor frame operator. So certain signals are badly characterized. And I'm staying away from the critical line because there either dimensions are missing, and even if I could use the Sachs transform, so that's a topic I should come back, we will not, it's not practical. And also there's no way to go to the limit in the continuous setting and so on. Okay, I think it's the point way to stop with my examples here, and to mention that I hopefully will be able to do something. For example, maybe one session could be related to a short session on the Sag transform, and the other session would be on the two-dimensional situation. There's the master thesis of one of my students who has done these examples, and where we used the zebra as an example for a nice test image. Yeah, okay, so I will stop the recording now.